Welcome back. Welcome to our ongoing discussion on logarithms. We've got one more series to talk through, and really, if I'm going to be honest with you, this section is the reason why we do logarithms with you guys at all. If it weren't for what we're going to talk about in this particular series, I wouldn't mess with logarithms in a Math 1010 course or something similar because it's just too academic otherwise. That said, though, because of these applications, it is imperative that you understand how they work. And we'll get to some progressively more and more complicated examples. Well, I say that. We'll get to some progressively more and more academic looking examples, but we'll ease into it. Let's start with a very simple argument here. This is something known as doubling time, where it's the time it takes for something to double. It can be money, as we have here, but it can also be populations like fish in a lake or bacteria in a culture. Anything that grows exponentially can be modeled under a doubling time equation. And that's what I've done here. Now, this part is true. A general rule of thumb for financial investments is if you don't want to worry about interest rates or recessions or booms or busts or anything like that, you just want to look at the long term. Long term is this: every 7 years, your investment, whatever it is, should be doubled. Now, obviously, not for like money in a checking account or something like that, but any serious financial investment like a retirement account or real estate, things like that, they generally tend to double every 7 years. Now, that doesn't mean that if you invest 1,000 now, it'll be $2,000 in 2027. Well, it does mean that, but it doesn't mean it will stay at $1,000 all the way up till December 31st of 2026, and then on January 1st it will double. It's an exponential process that grows progressively throughout that, but this 7 year mark helps you get benchmarks, helps you get an idea of what you can expect without having to actually do the algebra. So I've given you some benchmarks here. Every 7 years, it's going to be twice as much as it was before. And so in equation form, we've got A is equal to P times 2 to the T over 7, right? T being time in years, and I'm dividing by 7 because I want every 7 year period. P is however much you start with. And that's doubling time. So my question to you is this. Suppose I want to retire in 30 years with $2 million. I've got 35K saved right now. Am I good? Right? I just want to do napkin math right now, as it's called. I don't want to bust out the interest rates or anything like that. I just want to find out, am I good with this? And if I'm not good, how long am I going to need to work? So to find out if I'm good or not, let's just substitute into our equation here, right? Our starting amount, it needs to be an A there, sorry. Our starting amount is 35,000. 2 to the T, 30 years, over 7. And you run this through a calculator, you'll find about $683,000. Now, I don't need to explain to you that that is less than the $2 million we were shooting for. So this is not good. This is not even a third of what we want. Now, had it been $1 million, then the follow-up question would have been real easy, because I would know that once I've got that $1 million, it's 7 more years to hit 2 million. But I don't have that. So to find the time needed to hit $2 million, I might have to do a logarithm. So I got $2 million equaling 35K times 2 to the unknown T over 7. And from there, well, I'm just going to divide this 35,000 to both sides. So I get that's about 2 million divided by 35,000, equaling 2 to the T over 7. Oh, I've got an exponential. Let me undo that with the appropriate logarithm, base 2. Right? Whenever we do log base 2 of 2 to the power of something, I'm left just with that power. Specifically T over 7 in this case. So now I just multiply that by 7, and I'll have T is equal to 7 times log base 2 of this number, which a calculator can tell us. And if it's not a smart calculator, we can do a change of base. But anyway, we'll find 41 years here, which ain't great. That's 11 more years than we were expecting. This is a start.